Hello all, today we are going to start unit 3 of digital image processing is image segmentation. First, what is meant by image segmentation? Image segmentation is a method in which a digital image is broken down into various subgroups called image segments, which help in reducing the complexity of the image to make the further processing or analysis of the image simpler. Segmentation, in easy word, is assigning the labels to pixels. The primary goal of image segmentation is to simplify the image for easier analysis. Segmentation subdivides an image into its constituent region or objects. The labels of details to which the subdivision is carried depend on the problem being solved. That is, segmentation should stop when the object or regions of interest in an application have been detected. For example, in the automated inspection or of electronic assemblies, interest lies in analyzing the images of products with the objective of determining the presence or absence of specific anomalies such as missing components or broken connection path. There is no point in carrying segmentation past the levels of details required to identify those elements. The simplest method of image segmentation is called the thresholding method. This method is based on a clip level or a threshold value to turn a grayscale image into binary image. The key of this method is to select the threshold value or the values when multiple levels are selected. Segmentation of non-trivial image is one of the most difficult tasks in image processing. Segmentation accuracy determines the eventual success or failure of computerized analysis procedures. For example, a common application of image segmentation in medical imaging is to detect and label the pixel in an image or voxel of a 3D volume that represent a tumor in the patient's brain or other organ. This is a simple example to explain the image segmentation, how the image segmentation can be performed. In some situations, such as in industrial inspection application, at least some measure of the control over the environment typically is possible. The experienced image processing system designer invariably pays considerable attention to such opportunities. In other applications, such as autonomous target acquisition, and the system designer has no control over the operating environment, and the usual approach is to focus on selecting the type of sensors most likely to enhance the object of interest while diminishing the contribution of irrelevant image details. A good example is the use of infrared imaging by the military to detect the objects with the strong heat signatures such as equipment and the troops in motion. This is the example to explain the image segmentation. Most of the segmentation algorithm in this chapter are based on one of the two basic properties of intensity values, that is discontinuity and similarity. In the first category, the approach is to partition an image based on abrupt changes in intensity such as edges. The principal approaches in the second category are based on partitioning an image into regions that are similar according to the set of predefined criteria. Thresholding, region grooving, and the region splitting and the merging are the example of the method in this category. In this chapter, we discuss and illustrate the number of these approaches and show that improvement in segmentation performance can be achieved by combining the method from distinct categories, just as techniques in which the edge detection is combined with thresholding. We discuss also image segmentation based on the morphology. This approach is particularly attractive because it combines the several of the positive attributes of segmentation based on the techniques presented in the first part of the chapter. We conclude in this chapter with a brief description on the use of the motion cues for the segmentation. Then next point is why the image segmentation is necessary. The image segmentation is a large aspect of computer vision and has a many application in numerous industries. Some of the notable areas where the image segmentation is used is profusely are face recognition, for number plate identification, for image based search, and for medical imaging. These are the applications where the image segmentation is mostly used. Then our next topic is what are the fundamentals of image segmentation. Let's consider the R represent the entire spatial region occupied by an image. We may vary the image segmentation as the process that partitions R into n subregions, that is R1, R2 up to dash 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 Rn, such that is here the symbol U like represent the union, and while the symbol invert of U represent intersection. First, Ri is a connected set, that is from I is equal to 1 comma 2 comma up to n, where next one is Ri intersection Rj is equal to null. Phi is nothing but null for all I and j, where I is not equal to j. This mathematical expression or represent the where the image segmentation is complete or incomplete. Here Q of Rk is a logical predicate defined over the points in the set Rk, and phi is a null set. The symbol U and invert U represent the set union and intersection respectively. The two regions Ri and Rj are said to be the adjacent, or if their union forms a connected set. Condition A indicates that the segmentation must be complete, that is every pixel must be in a region, while the condition B requires the point in the region be connected in some predefined sense. That is example, the point must be 4 or 8 connected. Condition C indicate that the region must be disjoint, while the condition D is deals with the property that must be satisfied by the pixel in a segmented region. For example, Q of Ri is equal to true if all the pixels in Ri have the same intensity level. Finally, the condition E indicate that the two adjacent regions where Ri and Rj must be different in sense of a predicate Q. Thus, we see that the fundamental problems in segmentation is to partition an image into regions that satisfy the preceding condition. Segmentation algorithm for monochrome images generally are based on one of the two basic categories dealing with the properties of intensity values, discontinuity and similarity. In the first category, the assumption is that the boundaries of the region are sufficiently different from each other and form the background to allow the boundary detection based on the local discontinuities in intensity. There are three general approaches to segmentation. First one is thresholding, next one is edge-based method, and last one is region-based method. These are the three general approaches used for the segmentation. We discuss one by one. First one is thresholding. In thresholding, the pixels are allocated to categories according to the range of the values in which a pixel lies. The pixel with the values less than the 128 have been placed in one category and the rest have placed in the other category. The boundaries between the adjacent pixel in a different categories has been superimposed in white on the original image. It can be seen that the threshold has successfully segmented the image into the two predominant fiber type. This is all about the thresholding. Then the next approach is used for the segmentation is edge-based segmentation. In edge-based segmentation, an edge filter is applied to the image. The pixels are classified as edge or non-edge depending on the fiber filter output, and pixels which are not separated by an edge are allocated to the same category. And the last one approach is used for the segmentation is the region-based segmentation. The region-based segmentation algorithm operate iteratively by grouping together pixels which are neighbors and have a similar values and splitting group of pixels which are dissimilar in value. These are the three basic approaches used for the image segmentation. This figure represents the In this figure, the figure A represents the image containing a region of a constant intensity, while the figure B is showing the boundary of the inner region obtained from the intensity discontinuities. C is the result of segmenting the image into two regions. D is the image containing the texture region. E is the result of edge computations. Note the large number of small edges that are connected to the original boundary, making it difficult to find a unique boundary using only edge information. While the F is the result of segmentation based on the region property. This figure is represent. In figure A shows an image of a region of a constant intensity superimposed on a darker background, also of a constant intensity. These two regions comprises the overall image region. Figure B shows the result of computing the boundary of an inner region based on the intensity discontinuities. Point on the inside and the outside of a boundary are black, that is 0, because there are no discontinuities in intensity in those regions. To segment the image, we assign one label, say white, to the pixel on or interior 2. The boundary and the other label, say black, to all the points extended to the boundary. Figure C shows the result of such procedure. We see that the condition A through C stated at the beginning of this section are satisfied by this result. The predicate of a condition D is if a pixel is on or inside the boundary, the label is white, otherwise the label is black. We see that this predicate is true for the point label black and white in figure C. Similarly, the two segmented regions, object and the background, satisfy the condition E. The next three images illustrate the region-based segmentation. The figure D is similar to figure A, but the intensity of the inner region from a texture pattern. The figure E shows the result of computing the edges of these images. Clearly, the numerous spurious changes in intensity make it difficult to identify a unique boundary for the original image because many of the non-zero intensity changes are connected to the boundary. So, edge-based segmentation is not a suitable approach. We note, however, that the outer region is constant, so all we need to solve this simple segmentation problem is a predicate that differentiates between texture and constant region. The standard deviation of pixel values is a measure that accomplishes this because it is a non-zero in areas of the texture region and zero otherwise. The figure F shows the result of dividing the original image into subregions of a size 4 by 4. Each subregion was then labeled white if the standard deviation of its pixel was positive, that is, if the predicate was true, and zero otherwise. The result has a blocky appearance around the edge of the region because group of 4 by 4 square were labeled with the same intensity. Finally, note that this result also satisfies the 5 conditions stated at the beginning of this section. This is all about the figure explanation. The focus of this section is on segmentation methods that are based on detecting the sharp local changes in intensity. The three types of image features in which we are interested are isolated points, that is, isolated points, line and edge detection. We discuss one by one. First one is edge detection. Before that, we discussed in short about what is the point, line and edges. Edge pixels are the pixels at which the intensity of an image function changes abruptly, and edges or edge segments are a set of connected edge pixels. Edge detectors are the local image processing method designed to detect the edge pixel. A line may be viewed as an edge segment in which the intensity of a background on either side of the line is either much higher or much lower than the intensity of the line pixel. In fact, we discuss in the following section, that is, line gives rise to the so-called roof edges. Similarly, an isolated point may be viewed as a line whose length and width are equal to 1 pixel. This is all about the point, line and edge. Then we are discuss one by it what is meant by edge detection. First one is what is meant by edge detection. The edge-based segmentation is one of the most popular implementation of segmentation in image processing. It focuses on identifying the edges of a different object in an image. This is a crucial step as it helps you to find the features of the various objects present in an image, as edges contain a lot of information you can use. Edge detection is widely popular because it helps you in removing unwanted and unnecessary information from the image. It reduces the image size considerably, making it easier to analyze the same. Algorithms used in edge-based segmentation identify edges in an image according to the differences in texture, contrast, gray level, color, saturation, and other properties. You can improve the quality of your result by connecting all the edges into edge chain that match the image borders more accurately. Averaging in analogous to integration, it should come as no surprise that abrupt local changes in intensity can be detected using derivative. For reasons that will become evident shortly, first and second order derivatives are particularly well suited for this purpose. A derivative of the digital function are defined in terms of differences. There are various ways to approximate these differences, but in here we explain as we require that any approximation used for a first derivative must be 0 in areas of a constant intensity. The next one is must be non-zero on the onset of an intensity step or ramp, and third one is must be non-zero at a point along an intensity. This is the approximation used for the first order derivative. Similarly, we require that the approximation used for the second order derivative is that first one is it must be 0 in areas of a constant intensity. Second one is it must be non-zero at onset and end of an intensity step or ramp. And third one is must be 0 along the intensity ramp. Because we are dealing with digital quantities whose values are finite, the maximum possible intensity change is also finite, and the shortest distance over which a change can occur in between adjacent pixels. We obtain an approximation to the first order derivative at the point x of a one-dimensional function f of x by expanding the function f of x plus del x into a Taylor series about x, letting del x is equal to 1. Keeping only the linear terms, the result is the digital difference, that is del f by del x is equal to f of x plus 1 minus f of x. Here del f upon del x is also known as f dash of x. We used a partial derivative here for consistency in a notation. When we consider an image function of two variables, that is f of x comma y, at which time we will be dealing with the partial derivatives along the two spatial axes. Clearly, del f by del x is equal to df upon dx, where f is a function of only one variable. We obtain an expression for a second derivative by differentiating the first order derivative equation, that is del f by del x. The second order derivative for del f by del x is del square f by del x square is nothing but del f dash of x upon del x is equal to f dash of x plus 1 minus f of x is nothing but f of x plus 1 plus f of x minus 1 minus 2 f of x. This is a second order derivative. It is easily verified from the equation 1 for the first order derivative and equation 2 for the second order derivative that it satisfies the conditions stated at the beginning of this section regarding the derivatives of the first and the second order. This is also to highlight the fundamental similarities and differences between the first and the second order derivative in the context of image processing. Let us consider the figure. The figure A shows an image that contains the various solid objects, a line and a single noise point. The figure B shows a horizontal intensity profile scan line of an image approximately through its center, including the isolated point. The transition in intensity between the solid object and the background along the scan line show two types of edges, ram edges on the left and the step edges on the right. Intensity transition involving thin objects such as line often are referred as a roof edges. Figure C shows a simplification of the profile with just enough points to make it possible for us to analyze the numerically how the first and the second order derivatives behave as they encounter a noise point, a line, and the edges of the objects. In this simplified diagram, the transition in the RAM spans 4 pixels. The noise point in the single pixel, the line is the 3 pixel thick, and the transition of the intensity step take place between the adjacent pixel. The number of intensity levels was limited to 8 for simplicity. Consider the properties of the first and the second order derivative as we traverse the profile from left to right. Initially, we note that the first order derivative is non-zero at onset and along the entire intensity RAM, while the second order derivative is non-zero only at the onset and end of the RAM. Because edges of the digital images resemble this type of transition, we conclude that first order derivative produces thick edges and the second order derivatives much finer ones. Next, we encounter the isolated noise point. Here, the magnitude of the response at the point is much stronger for the second than for the first order derivative. This is not unexpected because a second order derivative is much more aggressive than the first order derivative in enhancing the sharp changes. Thus, we can expect second order derivative to enhance the fine details including noise much more than first order derivatives. The line in this example is rather thin, so it too is fine details, and we see again that the second derivative has a larger magnitude. Finally, note in both the RAM and the step edges that the second derivative has the opposite signs, that is negative to positive or positive to negative, as it transitions into and out of an edge. This double edge effect is an important characteristic can be used to locate the edges. The sign of the second derivative is used also to determine the whether an edge is a transition from the light to dark, that is negative second derivative, from dark to light, that is a positive second derivative, where the sign is observed as we move into the edges. In a summary, we arrive at the following conclusions, that is, first order derivative generally produces thicker edges in an image. Second one is second order derivative have a stronger response to fine details such as thin line, isolated points, and noise. Third one is second order derivative produces a double edge response at RAM and step transition in intensity. Fourth one is the sign of the second derivative can be used to determine whether a transition into an image is from light to dark or dark to light. This is the conclusion we arrive from above topic. The approach of choice for computing the first and the second derivative at every pixel location in an image is to use the spatial filter. For the 3x3 filter mask in above figure, the procedure is to compute the sum of the product of the mask coefficient with the intensity values in the region encompassed by the mask. That is, with a reference of the equation, The response of the marks at the center point of the region is, that is R is equal to W1 Z1 plus W2 Z2 plus dash 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 up to WNM ZNM, means up to infinite, from summation from values from I is equal to 1 to 9 or NM is equal to WI ZI. The figure shows the representation of the general 3x3 filter mask, where Z of I is the intensity of the pixel whose spatial location corresponds to the location of the ith coefficient in the mask. The details of implementing this operation over all the pixels in an image. In other words, the computation of the derivatives based on the spatial marks in a spatial filtering of an image with those marks are explained in this section. Then our next topic is detection of isolated points. We know that the point detection should be based on the second derivative. That implies using the Laplacian, that is del square f of xy is equal to del square f upon del x square plus del square f upon del y square, where the partials are obtained using, that is del square f of xy upon del x square is equal to f of x plus 1 y plus f of x minus 1 comma y minus 2 f of xy. Then the Laplacian is then del square f of xy is equal to f of x plus 1 comma y plus f of x minus 1 comma y plus f of x comma y plus 1 plus f of x comma y minus 1 minus 4 of f of x comma y. Using the Laplacian marks in above figure, which is the same as we say that the point has been detected at the location x comma y on which the mask is centered if the absolute values of the response of the mask at that point exceeds a specified threshold. Such points are labeled 1 in the output image and all others are labeled 0, thus producing a binary image. In other words, the output is obtained using the following expression, that is g of x comma y is equal to 1 if a magnitude of r of x comma y is greater than or is equal to t and 0 otherwise, where g is the output image, t is the non-negative threshold. This formulation simplifies measure the weighted difference between a pixel and its 8 neighbors. The idea is that the intensity of an isolated point will be quite different from its surrounding and thus will be easily detectable by this type of mask. Only the differences in intensity that are considered of interest are those large enough as determined by t to be considered isolated point. Note that, and visible for the derivative mark, the coefficient sum to 0, indicating that the mask response will be 0 in areas of a constant intensity. We illustrate the segmentation of isolated points in an image with the aid of figure B, which is an X-ray image of a turbine blade from a jet engine. The blade has a porosity in the upper right quadrant of the image, and there is a single black pixel embedded within the porosity. The figure C is the result of applying the point detector marks to the X-ray image, and the figure D shows the result of using the equation with the t equal to 90% of the highest absolute pixel value of an image. In figure C, the single pixel is clearly visible. In this image, the pixel was enlarged manually to enhance its visibility. This type of detection process is rather specialized because it is based on abrupt intensity changes at a single pixel location that are surrounded by a homogeneous background in the area of the detector mask. When this condition is not satisfied, other methods discussed are more suitable for detecting the intensity changes. Then our next topic is line detection. In image processing, the line detection is an algorithm that takes a collection of n edges points and finds all the lines on which these edges points lie. We know that for line detection, we can expect second derivatives to result in a stronger response and to produce the thinner line than first derivative. Thus, we can use the Laplacian marks in above figure for line detection. The figure A shows a 4 486 by 486 binary portion of a wire bond marks for an electronic circuit. The figure B shows its Laplacian image. Because the Laplacian image contains the negative values, scaling is necessary for a display. As magnified section shows the mid-gray represent 0, darker shade of gray represent the negative value and the lighter shades are positive. The double line effect is clearly visible in the magnified region. At first, it might appear that the negative values can be handled simply by taking the absolute value of the Laplacian image. However, the figure C shows this approach doubles the thickness of the line. A more suitable approach is to use only the positive value of the Laplacian. In a noisy situation, we use the value that exceed a positive threshold to eliminate the random variations about 0 caused by noise. As the image in figure D shows, this approach results in a thinner line, which is considerably more useful. Note in figure B through D that when the lines are wide with respect to the size of the Laplacian mask, the lines are separated by a 0 value. This is a unexpected. For example, when the 3x3 filter is centered on the line of a constant intensity 5 pixel wide, the response will be 0, thus producing the effect just mentioned when we talk about the line detection, as the assumption is that the lines are thin with respect to the size of the detector. Lines that do not satisfy the assumptions are best treated as regions and handled by the edge detection method. Let us consider the marks in figure. Suppose that an image with a constant background and containing the various lines oriented at 0 degree, plus minus 45 degree and 90 degree is filtered with the first marks. The maximum response would occur at an image location in which a horizontal line passes through the middle row of the mask. This is easily verified by sketching a simple array of ones with a line of a different intensity, say 5s, running horizontally through an array. A similar experiment would reveal that the second marks in respond base to line oriented at plus 40 degree, and the third marks to vertical lines, and the fourth marks is the line to line in the minus 45 degree. The preferred direction of each marks is weighted with a larger coefficient, that is 2, than other possible directions. The coefficient in each mark sum to 0, indicating a 0 response in an area of a constant intensity. Let R1, R2, R3 and R4 denote the response of a mask in figure from left to right, where Rs are given by the equation. R is equal to W1Z1 plus W2Z2 plus dash 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 plus up to Wn9Z9, that is summation of k is equal to 1 to 9 Wk/Zk. Suppose that an image is filtered with the 4 masks. If at a given point in an image magnitude of Rk is greater than magnitude of Rj, for all j is not equal to k, that point is said to be more likely associated with the line in the direction of the mask k. For example, if at a point in the image magnitude of R1 is greater than magnitude of Rj, for j is equal to 2, 3, 4, that particular point is said to be more likely associated with a horizontal line. Alternately, we may be interested in detecting line in a specified direction. In this case, we would use the marks associated with that direction and threshold its output, as in equation. In other words, if we are interested in detecting all the lines in an image in the direction defined by the given marks, we simply run the marks through the image and threshold the absolute value of the result. The points that are left are the strongest responses, which for the lines 1 pixel thick correspond closest to the direction defined by the marks. This example illustrates this procedure. This is all about the line detection. Thank you.